I'm Frank, this is your co-host Payman. We're going to talk about deep learning more, and it's still fall. Although night skiing opens in Cyprus tonight, so maybe I'll see some of you on the slopes. I wear orange trousers and wear green and black skis. You'll notice me falling mostly quickly. Anyway, last time we talked about deep learning, introduced the idea. It's a pretty simple idea, really. Right. The first thing you might, okay, what is it? You've got a neural network, right? The idea is that you learn your feature. You learn your features and your classifier simultaneously. So you learn your latent factor model parts W and the classifier or regressor weights V at the same time. You can think of this as learning features for supervised learning simultaneously. And the critical part is that in order for this to not be just another crazy parameterization or unnecessary redundant parameterization of a linear model, you need these nonlinearities. Okay, and we talked about basically sigmoid activations for those nonlinearities, motivating them in a couple of different ways. In theory, with a nonlinear activation, it makes such a neural network, given that the dimension of Z is sufficiently large, K goes to infinity, then this is capable of being a universal approximator, i.e. Approximating any nonlinear function from X to Y. We also motivate it from the biology perspective, saying that in particular with the nonlinear activation function, it's kind of like the action potential, basically the threshold before an action potential is released down the axon. And we said you can think of, in particular, when we get multiple layers of such a deep network or such a neural network, learning a hierarchical parts-based representation for whatever the data item is. Deep learning is sort of obvious from this point forward, which is you just keep adding layers. More generally, you should really think about more complex computation diagrams that might have edges from here to here or whatever. You can basically do whatever you want, really. The point though that we're going to do is we're going to do a layer by layer deep learning thing, and then on Monday, when I give sort of an optional but I think quite valuable lecture on automatic differentiation, you'll start to see that really what we're talking about is differential programming and computation graphs, and we want to be able to propagate gradients in such a graph. So in this like cursory early view on what deep learning is, which is basically good enough to get most of the intuitions across, a deep neural network is just a deep layer-wise, linear layer, nonlinear activation, another linear layer, nonlinear activation, and then a classifier layer on the end. And the main point is that you get unprecedented performance on difficult problems, right? Fine. Including ImageNet, which kind of was the dam which held back, the deep learning revolution, and basically introduced the deep learning revolution starting in about 2012. If I remember correctly. So what's ImageNet about? Well, it's a standard benchmark problem that was well designed to test computer vision algorithms and techniques, consisting of millions of hand-labeled images. Think about that for a second. It's a non-trivial thing to do. Get 1,000 people to label 1,000 images. It's a massive resource and still very much used today as a source of information. So the idea is that you have millions of labels, and there's lots of different kinds of computations within ImageNet, but one of the basic ideas that there are 1,000 identified object classes, and you can either look at the images as being labeled with a single predominant label, or as being multiply labeled with different stuff in them, or not so much multiply labeled, but it certainly has bounding boxes for the different objects. So you want to be able to localize and classify. Okay. And obviously, this is one of those AI complete kind of applications where it's really easy for humans to do it, but very, very hard for computers, or was like unfathomably, unimaginably hard for a long time. Okay, so in the object detection task, which is basically actually just an object classification or image classification task, you assign one label per image. Okay, so I mean, I would really call this, you know, it's object detection, but it's image classification, right? Not to localization, right? So image classification task, you get a single label, and the labels are dense enough. In other words, the specific classes of objects that are sufficiently difficult to distinguish that humans actually get around 5% error on this. So, you know, if I blanked out, you know, which of these was a Siberian Husky and which of them was a Canadian Husky, I would, unless there were connoisseurs in the class, I would be willing to bet that many of us would get that labeling wrong. Okay, so the techniques, the tools and techniques that we talked about throughout the evolution of this class: filter banks, nonlinear basis transformations, kernel methods, so on and so forth. Lots and lots of biologically inspired, you know, hierarchical parts models, so on and so forth. Everything you can imagine was thrown at this problem, and actually, in some sense, you could argue that we were doing pretty well, right? We were getting like 70+% of the images right in 2010 using classical techniques, and slowly over time, you know, every year since the advent of the ImageNet challenge, there would be a couple of % improvement, you know, maybe a different nonlinear basis, maybe a more sophisticated filter bank, so on and so forth. Was there a dominant classical technique? Yeah, filter banks and, you know, SVMs, filter banks and logistic regression, hierarchical filter banks, stacked models, these, all the stuff that we talked about. You know, imagine up to deep learning. We could give this as a final examination problem. The data scale is too large, but y'all would do a pretty good job, honestly, of you know, getting in this range using the tools that we've talked about in the class. Particularly if you think about convolutional feature extractors and that sort of a thing, like pyramids of feature extraction, multi-scale features. Like, you know, yeah, fine. And people would sort of ploddingly, trudgingly make progress a couple % of the time. But then in 2012, deep learning kind of started working. So there was a switch to deep learning. An 8-layer neural network was applied to this problem, and it gave rise to a very, very substantial jump in performance, right? There were some tweaks to this model, and deeper models were introduced, and in the span of 3 years, which is no time at all in the span of vision and modern artificial intelligence and machine learning, we went from you know, very, very subpar relative to human performance to basically near human level performance on this task. And you know, this 2014 model is Google and net, 6.7% error, 22 layers, blah, 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 okay? And this is, you know, what I mean by a deep neural network. This looks a little bit different than the things that we're talking about. It will be more understandable when we talk about automatic differentiation on Monday. But the basic idea is there's a bunch of linear layers, and by the way, it computes in this direction. So you take an image in and then does a bunch of different stuff, all of the layers, all of these filters, so on and so forth. But we're going to be looking at deep learning stacks like this, but you really should be thinking about directed acyclic graphs of vectorized operations and filtering of filter banks and all sorts of stuff. And we'll get to the last contentful lecture is Monday, but that's an optional lecture, is this Friday, when we're going to talk about convolutional neural nets. And basically there's a whole lot of convolutions going on here. And even in fact, the final loss is computed 3 times in this particular network in order to help preserve gradient strength. There's all sorts of stuff that went on in this model. Okay, so on this same task, In 2015, it was won by Microsoft Asia, achieving better than human performance. This model is 152 layers deep and introduced residual connections, leading to the name of ResNets. ResNets are used all the time. We use them in my research now. It also won localization, in other words, finding where the images, objects are in the images. Then after that, it was kind of mop up detail, right? So you can improve on all of that by ensembling. And then in 2017, people were like, "This is uninteresting. We have superhuman performance. You know, let's call it a day and move on to more challenging problems." And there are much more challenging problems that. So don't think that AI is solved because this is solved. There's plenty of very, very challenging problems. But yeah, cool. Questions, comments? Did they withhold the test set for ImageNet? Yes, they did. But there is a systematic field-wide overfitting on ImageNet. So if the basis of the question is, could people cheat? The answer is not easily, no, and the answer is no, but by virtue of testing on the same problem effectively for, you know, a decade, yes, there is sort of an architectural overfitting to ImageNet, and there certainly is a field-wide overfitting on the problem of image classification, which is an important problem, but not the only problem by far. Good question, though. Okay, so today, basically, it's pretty simple. Again, it's really, once you have some facility for computing gradients, it's really simple. And in fact, actually, I think, you know, Payman probably has I'm guessing based on, you know, his age and background, he's probably trained a bunch of neural networks, and you can chime in and say as much as you want to in this lecture. It's gonna help this, you know, that's totally fine. So today we're gonna basically focus on some practical issues. We're gonna talk about how to do backpropagation to compute gradients in the in a deep neural network. Again, we're going to sort of be very hand-waving quick about it because on Monday I'll do automatic differentiation, which is the real deal. Then, yeah, once we know how to compute gradients, and we'll talk about some issues with stochastic gradients and training deep neural networks. We'll talk a little bit about regularization, which is still controversial a little bit in deep neural networks. And then next lecture, Friday, we'll talk about convolutional neural networks, which can be viewed as a special restriction, basically a way of restricting the linear layer, the structure of the linear layers to make it lower dimensional in terms of parameterization, leading to less overfitting. So a couple of little details to put out there before we talk about gradients. When we did linear regression, we talked about adding bias to account for an offset, right? And we said that we could avoid this by, avoid this extra parameter by adding a column of 1s to x. In neural networks, we often want a bias on the output, and we often want biases on each of the individual hidden unit dimensions that I see. So these allow those individual parts to be biased towards being present or not, because we know that they're going to be shoved through some sort of nonlinear activation function H, and having those biases there help quite a lot. Okay, so this is equivalent to adding to the vector hz an extra value, which is always 1, right? Or if you're using sigmoids, you can equivalently make one row of the w's equal to 0. Not a huge deal. Pictorially, what's going on is that you have a constant 1 quantity coming into the prediction for yi, and in the deep neural network, you have individual bias terms coming into each of the hidden unit values as well. This is really quite straightforward when you start talking about automatic differentiation. Okay. So I guess the big question is, how do we get gradients, right? And the honest answer is everybody now uses software to get them, right? The historical answer is the beginnings of the deep learning revolution basically coincided with software packages for computing gradients automatically, and prior to that, all sort of connectionist papers had the structure something like 1 page of introduction, 7 pages of gradient derivation, 2 pages of results. Okay, so the automation of this backpropagation or gradient computation process was critical, although really at the end of the day, all you're doing is applying the chain rule with some bookkeeping efficiencies. Okay, so to train, normally we just use stochastic gradient or some variant of stochastic gradient, where we compute the gradient on an example or a mini batch and then update all the parameters in the network here, just V and W. It should be pointed out, because of the nonlinearity, we're not talking about plain linear regression anymore. This is a nonlinear, highly non-convex optimization problem, and optimizing it correctly, whatever that means, is both computationally difficult, but also sort of art and practice difficult in some cases. Okay, so computing the gradient, the way to compute the gradients in deep neural networks and in general computation graphs of the form of deep neural networks efficiently, it can be done using an algorithm called backpropagation. Backpropagation is a specific instance of automatic differentiation, which actually predated backpropagation. And there's again, we'll talk about automatic differentiation on Monday, where I think this gets much clearer, but whatever. So at a high level, what do we do to compute neural network gradient? Well, first of all, so here's our input and here's our output, right? Here up at the top, right? So the first thing that we do is we do need to do a forward propagation, right? We, compute Zi1 from X, we compute Zi2, the second layer from Zi1, we compute Y hat, pushing through the nonlinear functions. And remember that there's just a matrix multiply here with W1, I guess, and W2 here, something like that. Okay, and I just stomped on my other build-ins, but that's fine. In backpropagation, basically what you do is you pass gradient information, basically an adjoint, backwards along the computation graph in a very particular way that allows you to compute the partial derivatives that you need in one step after another, using combinations of bits of information from the forward pass and combinations of gradient information from the backwards pass. Okay, so we compute the gradient of the loss with respect to V, and then you use that plus forward information to compute the gradient with respect to ZIM and the weights, and so on and so forth. So all intermediate bits of the computation, you compute the partials with respect to those, and those in turn allow you to compute the partials with respect to everything further forwards in the original computation graph. So, like, these are the first steps, and then these are the last gradients that you compute on the way out. Okay, basically, if we say, okay, go to town, you could figure out backpropagation on your own using your favorite rules of multivariable calculus and the chain rule, provided that you find the right little bits. And this is the nice part about automatic differentiation and backpropagation, provided that you find the right bits for doing the bookkeeping to keep the computation efficient. So we're going to just give a very brief idea about what's going on in backpropagation and a 1 training example, 3 hidden layer, 1 hidden unit, like basically scalar hidden unit neural network. And then again, on Monday, we'll do automatic differentiation, which will give you a better sense of what's really going on under the hood. Fine. So our loss is a loss with respect to all of these parameters, right? W's, all of the weights, W, and final V. And again, everything is scalar here, so it's simple to think about. We're going to use, we're recognize that our prediction y hat I is the composed, application of a matrix multiply, a nonlinearity, a matrix multiply, a nonlinearity, and so on and so forth. Okay, so that's what's going on here. X times W1, so on and so forth. Okay, going up. If we want to take compute the partial with respect to V, which is going to be part of the gradient of F with respect to all of its parameters, and we identify that this thing, our favorite thing, is the residual R, right? Then, when we take a derivative of this expression, it's just the chain rule, right? So this 2 is going to come down, it's going to cancel, and we're going to get the inside times the derivative of the inside with respect to V, and the derivative of the inside with respect to V only has this term, right? Okay, so df dv is just R times all of that, right? Fine, okay. Now this is where, the lining up, this is a little bit too imprecise in this. So we'll, again, automatic differentiation is going to do this. This is where the lining up starts to happen, right? So you'll notice that the gradient of F with respect to V, the partial of F with respect to V, requires information from.
Where did R come from? Sorry.
R is just the residual. It's the difference between y hat I and yi. That's all. Okay. Sorry for covering it up with a pencil. So you'll note that R is sitting here. So this is R, right? So R is available above V, and H of Zi3 is available below V. Okay. So we can take information from the forwards pass and the backwards pass, and that's enough information for us to compute the gradient, the partial of the loss F with respect to V. Okay. Now, if we do the same thing and we take a partial with respect to W3, and we just do grody old school chain rule calculus, right? So we're going to get, the 2 is going to cancel, we're going to get R, and then we're going to get V times, H prime evaluated at its argument, and then we're going to take a derivative of the inside with respect to W3, and we get this, right? This bit right here. Fine, okay? So now we're looking at taking a partial derivative with respect to this parameter, right? So you'll note also, again, that if we pass the right stuff backwards, in particular, if we pass this stuff backwards, R times V, right, that we get from above, and we have available to us these partial derivative functions for the primitive operators. In other words, H is the sigmoid function. We can take a derivative of the sigmoid function with respect to its parameter and then evaluate it at some point. If we have this function H prime sitting around, in other words, the derivative of the sigmoid with respect to its argument, right? Then we have that local information here, and we have the information coming up from the original forward pass. Okay, so local to W, we have all the information we need in order to compute the partial derivative of the loss with respect to W, having already computed the stuff above it. Okay, so we can keep doing this, right? And so you can, one way, and this is the grody way to go get the gradients, is you can just literally, all we're doing is applying the chain rule. So at the end of the day, that's all that's happening. We're just applying the chain rule or taking a big derivative, right? But what we're noticing is that we can pre-compute, we can compute and store stuff on the way up and on the way back, and use only local information at a particular parameter, impinging on a local parameter to compute the gradient at that parameter. So R3 is just the product of the stuff that occurred before. That's the adjoint that's coming back, and then there's the local partial, and then there's the feed forward computation as well. Fine. Are these H functions always known or specified? Yeah, so again, so far we've talked about sigmoid. I've hinted at ReLU, and we'll talk about one more today. But really, yes, in general, you will pick these H functions, you know what they are. In the more general case of automatic differentiation, R3. Oh, R3 is just this. R3 is just the product of all this stuff. In general, what these H's will be, and one of the things that's a little bit, okay, we can take partial derivatives of stuff in linear computation graphs until our face turns blue, and it's going to look like this, and you're not going to see what's really happening. But because we're treating matrix multiplication as we're not identifying it as a primitive operation. Ultimately, H prime is going to be the derivative of the whatever primitive operations there are in this graph, and the primitive operations will include times and divide and matrix multiply and matrix inversion and whatever primitives you have in your language here. The only primitives that we're looking at are the H functions, which are these sigmoid functions. So again, you can do out you can compute gradients like this, but the point is that, if you, this stuff just keeps getting stuff multiplied onto it, right? So the bookkeeping is you want to keep that around and pass it backwards downwards in this case, through the H that I not show up on the right of last equation. Oh, have to. Yeah, okay, great. Yeah. So yeah, that's the plan. Okay. If we just copy over the final results of all of this, right? The point is that this information over here, well, yeah, depends, gets passed down, right? This information gets passed up, right? And you can compute locally the gradients that you need from information that travels in both directions. Okay. Also, only if you really care, like, only this R changes if you choose a different loss. So in other words, if you have one big, long, dense neural network and you happen to have hand derived all of this and you happen to have written a piece of code, you can change the final loss on your neural network without changing a whole lot of code. Doesn't really matter. So we did all scalars here. If you do multiple hidden units, you get extra sums from the law of total, the total derivative. And again, on Monday when we do here, yeah, this is R. We will see more clearly what happens here. Okay, fine. And yeah, the efficiency comes from basically storing all of the intermediate computation values in the forward path so that you can consume them in the backwards path. That's really where the efficiency comes from. So because we're going to do automatic differentiation, we've abbreviated this backpropagation stuff to the very, very, very bare minimum here. What you need to know is, you probably never actually have to implement any of this.
Convex?
Which loss function? No, the overall loss function with respect to all of the parameters is most definitely not convex because of the nonlinearities. Do you need to know how to do backpropagation? No, not anymore. It's, you call backwards on your favorite, PyTorch computation graph, and you get the gradient with respect to everything that you could possibly ever want. And that comes from this magic system, that a programming languages tool that predated backpropagation called automatic differentiation, and is basically a standard tool now. But understanding what's going on, in particular, understanding that when you're doing automatic differentiation or backpropagation, in order to do it efficiently, you need to store all of the intermediate results on the way forward through your computation. That you need to know about. In particular, you need to know that deep neural networks consume more memory than you might think, because they are storing all the intermediate results, right? You need to know what the computational cost is. So the forward pass is dominated by whatever computation you're doing here. That's all matrix multiplications by some weight matrices and a final classifier vector, parameter vector. So if we have m layers and all of the dimensions are of the hidden units are k, then the total cost would be the final layer inner product plus a bunch of matrix multiplies, m of them. The main point, though, that you need to know is that the backwards pass in an automatic differentiation system takes the same computation. It has the same computational complexity as the forward pass through the model. So to get a single gradient evaluation, you have to push the value forward through the network and pull it all the way back. Cool. Another nice thing, it should be relatively straightforward, right? So for multi-class or multi-label classification, that final layer, you replace the V with a matrix, and now it has a multi-headed output, right? And you can use the softmax loss that we talked about earlier in the term, where you exponentiate and divide through by all of the other elements. That it totally works, and now you have a multi-class classifier straight away. This in deep neural networking land is called this cross entropy for various reasons, which I actually sometimes prefer, but they're the same thing. Speaking of vocabulary, deep learning has a convoluted and sometimes confusing vocabulary. Deep learning or deep learning model is a model with many hidden layers. Usually they're neural networks. Sometimes they're more complicated things. A neuron is a node in this graph. A visible unit is usually an input feature. A hidden unit is one of the latent vector Z's, or the nonlinear transformation. An activation function is the nonlinear transformation. The activation itself is the application of the nonlinear transformation to the value of the latent factor. Backpropagation means computing the gradient of the neural network with respect to an example. Sometimes people very confusingly use backpropagation to mean training a neural network using stochastic gradient descent. Weight decay is, I think, the most annoying of all of the terminology in deep learning. It just means L2 regularization of the neural network weights. Cross entropy, again, you can argue about whether or not that's better than softmax, but it's the same thing. Learning rate is the stochastic gradient in step size. Learning rate decay means basically you change the learning rate over time, decreasing it as you go. And vanishing gradient refers to the problem of usually underflow of some kind, zeroing out your gradient computations. Questions at this point? Probably not many at this point. So relative to the ImageNet challenge, but otherwise more applicable. One of the organizers were friends with all of them, visited UBC in 2015. and was asked, besides a huge data set, a huge neural network, and a huge computational cluster, what's the most important aspect to solving these kinds of problems? And we've talked about this earlier, but just to remind you, this is super, super important. If you know that your model should be invariant to various transformations of the input, that's a free source of data, and you should use those transformations of your input in particular to augment your training data set such that you can train even larger models without overfitting. So rotating or translating or scaling or changing the lighting on of images is very, very useful. And then optimization and the kind of optimization algorithm you use is really, really important. And you get asked, why should optimization be so important? Well, the objectives that we're talking about are highly non-convex, and they get nastier in terms of optimization surfaces with depth. So the optimization choices that you make, it turns out that they're very highly correlated with the quality of the model and work. So out of curiosity, do you have a personal choice between PyTorch and TensorFlow? My whole group uses PyTorch, and very strongly I prefer PyTorch for my research purposes, because I do the deep neural networks that I use, or the situations that I use differentiable programming, are those that do not necessarily have computation graphs that are fixed length or defined in advance. So I thought deep learning didn't really need to have transformation stuff, or is that CNNs? So CNNs are a choice of architecture. This is a really good question. And CNN-based image recognition models or image classification models absolutely still need, in fact, maybe even more need the transformation stuff than other things like that. Will deep learning still, well, deep learning still has a set of parameters to learn, so you need transformations like convolution. So I think there's two levels of what's going on here. We'll talk about convolutional neural networks on Friday, and they're very, very simple. You can imagine what's going to happen. But the transformation, so if you have a convolutional neural network, which we're not going to talk about until Friday, you still have some deep neural network, some computational graph that goes from input to output. And if your inputs, like if you can change the scale of your image or rotate it ever so slightly and it still remains a dog, then you can get, a lot more training data of dogs and their labels by, providing all those translations and rotations, that kind of transformation to your training data. Of course, the neural network is going to do internal transformations of the data, including convolutions and that sort of stuff. But that does not limit the usefulness of these kinds of training data transformations. Okay, it's really, really important. Okay, okay. So the basic answer, and were we to run a pure deep learning course, I'm not sure that there's enough theory to run a full undergrad course on it. Maybe a grad course to read some papers. It hasn't really distilled down into an undergrad course. But what do we do for deep neural network training? Some variant of stochastic gradient. You choose an example I. You use backpropagation or automatic differentiation to get a gradient with respect to all the model parameters, and then you take a small step in the negative gradient direction. And here, Payman can probably share some of his personal horror stories. Right? It's not immediately obvious that stochastic gradient is going to work as a black box learning algorithm, right? And there's lots and lots of tricks and tools of the trade that people use to get deep learning systems to work. One thing that people thought a long time ago is, that training deep neural networks might be hurt by the presence of lots and lots of local minima, and maybe you don't actually do well because your loss surface is super ridiculously non-convex and you've got all these local minima. And there has been over the last couple of years some okay, yeah, whatever, close enough. There's some theoretical evidence that's starting to explain empirical findings that local minima are probably not the problem, actually. In other words, there's if you look for papers on what is it called, highly over-parameterized models, right? So if the network is deep or wide enough, there's some thinking that goes that, you know, all local minima are probably good and maybe even equivalent. The problem is that it still can be hard to actually descend into one of those using stochastic gradients. And if you think about what stochastic gradients is doing here, it's kind of insane that it even could possibly work, right? So these deep neural networks will have, you know, 10 million parameters, and you take a single instance and compute a gradient with a single instance or a very small mini batch, and you're saying you should move in this 10 million dimensional space this way, right? It's crazy that it works. You know, nobody in their right mind would have thought that it wouldn't. That's part of the reason why it took so long for people to do it, because nobody would try it because it seemed dumb. So parameter initialization is crucial, right? You can't you just have to be smart about how you start things out. You can't initialize the weights to all the same value. You can't initialize the weights too large, otherwise your gradients will be huge and you'll diverge right away, or it will take a really long time to learn. Standard thing to do is to do random initializations. You set the bias variables to 0, and then you set all the rest of them by sampling from a standard normal and divide by some big number. Turns out that multiple initializations usually does. I mean, we do them, but it's not that important for final test performance. It turns out that stochastic gradient, and here Payman can probably say a lot, right, is very sensitive to the step size, right? Now there are ways that there are modern stochastic gradient algorithms that help this a little bit, but it still is the case that you know, there's a certain amount of manual babysitting of step size that goes on. So you run your optimization algorithm for a little while, and you sort of descend rapidly into the ball of confusion, and then you say, oh, okay, I'm watching my validation or training error go down as I'm going along, and it sort of stabilizes. And then, well, if it's not decreasing, you decrease your learning rate, and you see actually that your loss decreases, and then you decrease it again, so on and so forth. So, you know, this is like graduate student logs into computer at 3 o'clock in the morning, graduate student logs into the computer at 5 o'clock in the morning and says, okay, restart, but start training with these values and use a different learning rate. Fine. There's, you know, you probably shouldn't use the same learning rate for all the variables in your model. Methods like Nesterov acceleration and other, you know, sort of momentum using methods have proven to be valuable. In other words, you know, if you have this crazy, you know, take a training example and compute a direction in 10 million dimensional space, it's probably a good idea to kind of average your gradients and move in the average direction of gradients. And that's basically what happens. There's your standard gradient update. And if you, you know, add a term that keeps you going in the old direction, and then you can see this as basically an exponential moving average of all of your last gradients. And what's it look like? Here we're going to look at just gradient descent. If you do gradient descent and you just follow the gradients with a small step size, you're just going to approach from the left. But if you use a heavy ball method where you're computing an average, you're going to keep, you know, keep going, you know, keep going in the and accelerate into the accumulated gradient direction. So basically, you'll end up bouncing around more, which is good in the sense that you get far faster, basically. Setting a step size is
same as stochastic gradient descent?
No. So the heavy ball method is exactly what we are showing here. You basically just accumulate your gradients and you compute a running average, a weighted running average of your accumulated gradients. Okay. So setting the step size, it turns out that the step size is super, super important. Couldn't choose the step size has to be automated depending on errors. read a fun paper called Hypergradient Descent and about 8 million other papers. So Mark and I wrote a paper together on like using automatic differentiation to differentiate through the learning procedure to set the step size automatically based on gradient approximation of the difference in error that you get from one step to the next. So yeah, there's a whole bunch of stuff. Using the gradient of the learning algorithm, right? So this is where automatic differentiation comes in. So it's not the gradient of the gradient, that's a second order method. That would be, you know, like a Hessian kind of a thing. It's the gradient of the learning procedure. It's a different thing. Look it up, it's fun. Hypergradient descent. So setting the step size is important. So one thing you can do is you can compute the complete gradient on a subset of the data, or compute it on a larger subset of the data one time, and then do a binary search for the step size that basically minimizes the loss using in that one particular direction, right? Then use that step size for a long time or decrease it for a little while. There are other optimization algorithms that pay attention to, you know, correlations between like use different step sizes for different variables and learn something about the correlations structure of the latent parameter space as you go. Adigrad, Armis, Atom. Often these will work well enough out of the box that you can just apply them. However, they seem to be losing a little bit of popularity to stochastic gradient, often with some sort of momentum, because it has been observed that there's a special magic property of SGD. It strikes again, we've seen it a couple of times during the course, which is that in terms of test error, SGD often actually does better. The noisier gradient, even though it takes a little bit longer and you have to manually tune step size, in terms of generalization error, the models learned by SGD are often better than super hyper optimized models using arrived at using Atom or Armis prop. And in fact, you can see that in the hypergradient descent paper, where we learn how to optimize stuff super fast and super well. But then when you look at test error, the models trained with stochastic gradient descent do better, which is confounding.
Can you explain batch stochastic batch SGD?
We went through that when we talked about stochastic gradient descent. It's basically you select a mini batch of data points and you compute the gradient of all of them and compute the average over the mini batch, average of the gradients evaluated for each of the elements in the mini batch. And as the mini batch size approaches the full data size, the variance of the gradient about the true gradient goes down clearly, right? And the correlation between the mini batch gradient and the full true gradient gets larger, right? Could it be because the stochastic gradient descent is less likely to converge on a local minima? In terms of folklore, that's basically the thinking, that the random walk of behavior of SGD somehow will only settle down in basins of attraction that are sort of broad and generalize well in some sense. So yeah, or does random initialization take care of this? Well, random initialization is going to put you near some local optimum. We don't know what that is, and the point is that there are, thanks to permutation symmetries in particular, an absolutely enormous number of equivalent local minima. Anyway, we should power on. We're basically nearly done. Again, same thing we just talked about. Bigger batch sizes give you faster convergence because you can use larger learning rates, and you can often optimize to better training loss, but they may not lead to, this is very counterintuitive and really at the cusp of deep learning theory, may lead to worse test results. There's a sort of a very hacky thing that's used all over the place is in order to make neural network learning more stable, the thing is called batch normalization, where you standardize the hidden units within a batch as you go. It's very weird, but it works and it stabilizes gradients that you can use for learning. Okay. This is the last thing that we need to cover before we go. I spent a long time talking and not a long time getting through stuff today, but it's pretty straightforward. So we've seen that away from the origin, if you use the sigmoid function, the gradient is nearly zero. This is we talked about this before. If you have a deep neural network that's constructed by composing lots of sigmoid activation layers, when you take a sigmoid to a sigmoid to a sigmoid, the resulting function gets even sharper, so there's less area where there's gradient signal. So what you do is you replace the sigmoid with ReLU, and this really is the other major ingredient that's led to the deep learning explosion, that and residual network, residual connections, because there's gradient signal everywhere over here in the positive orthant. So, I mean, the ReLU is just what you see here. Fixes the vanishing gradient problem, gives sparser activations, and unlike, you know, the sort of binary hierarchical parts-based model, original neuroscientific orientation that was like maybe spike time dependent in theoretical abstraction, here we can think about this as doing some sort of rate coding where you have a real valued rate code instead of a 1 or 0 activation. Fine. I'm just even going to skip this. There are other activation functions that you can consider, like a swish activation, and there's some evidence that maybe this does well, but it's weird, and everybody uses ReLU anyway. So, in summary, deep neural networking, cool. Gives you unprecedented performance on many difficult pattern recognition tasks. Backpropagation, automatic differentiation are how you get gradients with respect to parameters in deep neural networks. It's basically a very nice use of chain rule and the total derivative rule. And there's not much more to it, and it's basically available to you in packages now. Parameter initialization is important. You shouldn't do it in a dumb way, that's for sure. Optimization is hard, but doable, particularly with modern optimization packages. And ReLU, which is probably the most important thing in this lecture, allows you to avoid the vanishing gradient problem and actually train deep neural networks. And on Friday, we'll talk about convolutional neural networks, and that's it. Cool. What if we take some sort of Gaussian activation or like a delta function? If we make H you're very welcome. What do you mean by Gaussian activation? So you make H a nonlinear function, which is like a Gaussian at 0. Yeah, that would be nonlinear, but it's going to suffer it's going to it's going to suffer the same vanishing gradients problem. At all the tails. And if you had a Gaussian activation function, I think that this would not be a very particularly good, I think this could be worst case optimization land, because you'd have a trivial solution, which is to set all of the weights equal to 0, and that would maximize or minimize your loss, because, oh, that's not true. Yeah, I don't know. Try it. It doesn't make sense to me, but yeah, try it. Are there any disadvantages to using ReLU? Well, it's the same. This is the same kind of model selection, hyperparameter selection problem that we always have in this course, right? So there are going to be some problems for which that activation works well, and some problems for which other activation functions work better. There is the model family. It's part of the model family. So are there disadvantages to using ReLU? Yes, there are some problems for which ReLU is not going to give you the best possible neural network.
I think also the neurons can get clamped to zero, which all the way the weights will be it'll be outputted zero. So called
yes,
dying ReLU, I guess.
If you get into a situation where all of the activations put you in the negative orthant, then you have no gradient signal and learning is just not going to proceed. Yes. Yeah. And this is a situation where being smart about your initial parameterizations makes sense, right? So instead of Gaussian, you might want to, stick in uniform 0-1 activations or something like that, so you get or initial parameters, so you get positive signal straight away.
Yeah, I guess leaky ReLU also kind of addresses this, right?
Yeah, there's leaky ReLU, and then this switch thing would also address it, right? Yeah. Cool. All right. I think with that, we'll call it a day. Thank you all very much.